Hey guys, welcome to our classroom. My name is Andrew, and I am here with my two colleagues, Anish and Luke.
Hey y'all, I'm Anish.
Yo, 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 what is up, guys? I'm Luke.
We are chemical engineering students, and a big part of being a chemical engineer is having a solid understanding of feedback and control processes.
Today we will be showing you how to analyze a process control problem using both methods by hand and a cool program called Simulink.
Whether you want to be an engineer working at a refinery, a brewer working on fermentation, or even a scientist in the lab, process controls are necessary to prevent dangerous situations, such as runaway reactions, or even just to simply increase productivity.
We have chosen an average problem straight from one of our homework sets in order to show you how Simulink works.
Simulink can be used to model process responses in industry. Whether it's a temperature change in a reactor or a sudden disturbance in flow, it can accurately be predicted via Simulink very quickly.
Oftentimes, it is helpful to know how to do these problems by hand so that you can understand how to analyze more complicated systems or models in programs like Aspen, MATLAB, or Simulink, which we will be using today.
So let's get started. We chose to model a simple two-transfer function process with a time delay. We are using these transfer functions to model the response of a parameter change in a mixing tank. Before we get started in Simulink, we want to figure out how this process will be modeled by the transfer function. Let us start with a step input. A step input indicates a set change in a parameter at a certain time, which continues for the remainder of the process. Parameters that can change include temperature and level in the reactor, to name a couple. In this transfer diagram, US represents a step input.
Essentially, the step function is like a light switch to turn on the process, and the time delay determines when the light actually goes on. In the transfer model, the e raised to the negative theta s represents the time delay. Theta determines the time at which the input affects the system. So if we model our step change with a time delay of theta equaling 5, the response will occur after time equals 5 seconds or minutes, depending on your scale.
The transfer functions, for those who are unaware, represent how the system responds to different inputs. The transfer functions are these two equations in the boxes here. Each component in a system will have a distinct transfer function to model its response, and this will usually be given to you in any setting. In this example, there are two components influencing process response. When solving manually, we start by multiplying each transfer function together, as they are multiplicative when in series. This lets us use an overall single transfer function to model the entire system for convenience. I took the liberty of multiplying out the denominators beforehand, and we get a single transfer function of 4e to the negative theta s, mind my handwriting, all divided by 0.32 x to the fourth plus 2.08 x cubed plus 4.56 x squared plus 3.8x plus 1. I'll make that denominator a little bigger.
So now we can do this problem by hand to determine how our output parameter will change. The way we will model this is using the final value theorem, which will be written out now.
The final value theorem states that the final value of an output will be equal to the limit as s goes to 0 of s times y of s, where y of s represents our overall transfer function.
The final value theorem allows us to predict the output parameter. Our transfer functions have already been converted into the Laplace domain. So then we can take the limit of s going to 0 of this transfer function multiplied by the Laplace variable s, and we'll be able to find this final value.
So we will assume the input parameter changes from 300 to 310. A single unit step input is modeled by 1 over s So a change of 300 to 310 could be written as 10 over s. Multiplying our step input times our transfer function, and then multiplying it by the s in the final value theorem, which we can see what our final value will be.
Okay, so now we have our overall transfer function written out here, which is 10 over s multiplied by the rest of our transfer function. Now we are going to set s equal to 0 and cancel all the s terms. As we simplify, we notice the expression will simplify to a single constant. Notice that the 10 over s in the step input cancels out with the s from the final value theorem. If the limit were to result with 0 in the denominator, this system would be described as unbounded and there would be no final value to find. Similarly, if roots in the denominator are positive or imaginary, the system is also unbounded and there's no final value that can be found.
In this system, we will get a final value of 40 as our final output. This means the step change of 10 would yield an eventual change of the output of 40 as time goes to infinity. Let's draw the general response.
We have our time input at 5. Starts at 0, so nothing happens. And then at 5, we shoot up, and then we level off at our final value of 40. Now that we have a manual solution, let's check our work in Simulink. You will need to have MATLAB installed with the Simulink package. If you do not know if you have Simulink, just go into the MATLAB command window and type Simulink as shown. You can also go to the home page and there is a button for Simulink.
The button is here and you can type Simulink and enter into the command page and Simulink will pop up. You will also be able to download it if you don't already have it. So first, to create our model, we will want to create a blank model. Essentially, this is our canvas, and we can model a process in the same way we saw it manually depicted. Okay, so to start in our model, we want to get our step input, we would want to go to the library browser to find all of the different blocks that we can use to create our model. So first we want to find our step input, which would be found in sources. And if you scroll down, there's different inputs, including ramp, which is my personal favorite. And so dropping step into the process should result in a step input being added to the flow worksheet. We can drag blocks into the model and choose step inputs and choose different inputs as we go.
I personally find it easiest just to use the search bar instead of scrolling through every type of block in Simulink. If you know what you're looking for, this can save you a ton of time during the modeling process.
We will then need to add 4 transfer functions, a transport delay block to account for the 5-minute or second time delay, and finally a scope block in order to plot the results as time goes on. I personally think the scope block kind of looks like a character from Among Us. The scope allows us to see the system response after the simulation is run. Each block can be double-clicked to alter its components. We would want to use a transport delay.
Okay. So as mentioned, each block can be double-clicked to alter its components. Notice when creating transfer functions, we can only plug in the coefficients. Thus, a block denoting 2 over 2s plus 1 would have a numerator with the coefficient 2 only, as indicated here. And in the denominator, if there is a 2s plus 1, you would alter the first coefficient by changing this value here. Once you press OK, it should change in the block, and you should be able to see the system response. So we are going to go through and alter the parameters for all of the different blocks in our transfer function. First will be 2 over 2s plus 1. Then we will have 1 over 0.4s plus 1, which will be modeled here. Next, we'll, and you'll see numerator or denominator, and you might have to drag out to see the full block. Next will be 2 over 0.4s plus 1 again. And the last transfer function will be 1 over s plus 1. So it's already set as we want it. We also need to go in and make sure to change the time delay to 5, because that is the time delay we specified. Okay, so for this case, so we can set the time of our model to run for however long we want in the top, as you can see here where stop time is indicated. So let's set our runtime to 50 seconds. The x-axis of our plot will show, will eventually go to 50, and the y-axis will automatically scale to show us the entire response until a time end of 50.
It is often a good idea to set the time to a relatively high value to ensure that we see the entire picture. If a response does not look as good as expected, increasing the runtime can sometimes be helpful. Now we have to draw connecting lines between each block by dragging the arrows from block to block. This allows the program to know the order in which we are performing these operations in.
Once all of these have been done, we can run the simulation by clicking the green Run button at the top. You can also use Control or Command T on the keyboard to have the system save and run automatically. Let's see how our plot looks.
So you will want to double-click Scope to see how your process response looks. It might take a second. Amazing! It looks like our plot corresponds quite well with what we expected. We have no response until around a time equaling 5, at which you can see an increase. And this makes sense since we have a time delay of 5. The process takes off and we reach a final value of 40 as predicted. It seems like it takes about 15 seconds after our time delay for the final value to be reached.
This is great. Now you can use Simulink and the final value theorem to draw process responses. As you become more skilled in Simulink, you can create more complicated models and avoid having to solve them by hand. For now, it is great to have both skills in case you do not have access to programming.
Thanks for listening, and be sure to check out our other videos soon. Remember to like, comment, subscribe, and share with all of your friends for more epic Simulink content.